Yes, so as Jacek mentioned, I'm a PhD candidate at Gdańsk University of Technology, and my dissertation is focused on processing and improving quality of thermal images for the needs of remote medical diagnostics. And I also work for Intel in San Diego, and I'm responsible there for optimization of models for edge applications in smart home and in autonomous driving. So today we'll talk about convolutional neural networks. And this is a specific type of neural network that utilizes convolution operation. And these networks are known for a few decades right now, but only recently they gained more popularity because we have access to better computational power, we have access to huge data sets that we can feed our models with to achieve a good accuracy. And also the innovations and the progress in this research is progressing very fast, so we know a lot of tricks that can be used for more efficient training. So let's start with example of this image that we can see. When we look at it, we at once know that this is a turtle. This is kind of effortless for us, but in order to describe in pixel values what makes this object a turtle, it's more difficult. And actually, it would be nice to have a network that we can just feed the data with, that we don't have to define specific features by hand. We can just give the data and let the network learn what patterns are important. This is how our brain works. So the way how it works, and the way how it processes visual inputs served as an inspiration for development of CNNs. It all started with a research on neural activity in cats. This study was later awarded with a Nobel Prize and led to the discovery of a structure of primary visual cortex. This is a part of the brain which is responsible for processing visual input, and it's also known as V1. And it has been shown that V1 is a two-dimensional map which mirrors the retina structure. And when a light hits retina, only neurons that are within a small part of V1, and the small part of V1 corresponds to the part of retina where the light arrived, only this part of V1 is stimulated. And this small part, small visual field, it's called local receptive field. As we can see on this example, only a part of image is covered at once by this local receptive field. Another important finding was that V1 is composed of simple and complex cells. And simple cells are activated by simple pattern, which can be in some approximation characterized by linear function within this receptive field. This activity is modeled by a convolution operation. And the other type of cells are complex cells. They also respond to some features, but they are invariant to some translations of their shifts. And this feature is modeled by a pooling operation. These two operations, convolution and pooling, are the main building blocks of CNNs, and today we will learn about both of them. So let's start with convolution. What is convolution? We can see on the left of the slide that we have some input. It doesn't have to be image, but for simplicity, let's assume this is an image, and we have some pixel values here. And then we have a filter, also known as kernel, which has some values. These values are known as weights. And we want to produce the output. So what do? We place the kernel on our image in a way that the value for which we want to calculate the output will be placed in the middle of this kernel. So like here, for example, we want to calculate the output value for this one. So we will place the kernel here, and we will compute the output for this location. How do we do it? We sum all pixels within this receptive field weighted by the kernel weights. So we take this input value 0 multiplied by 0 plus this input value 1 multiplied by 1, and so on and so on. We add all of these values to produce the output. And we have 3. What do we do next? We move the kernel, the filter, across our image to calculate the next output value. And because we use kernels to extract some patterns, some features, we call the output a feature map. What's also important, convolution is usually denoted with asterisk operator, like here. Okay. And during the previous lecture, we've learned about standard neural networks, for example, MLP in particular. So it's important to talk about some differences between convolutional neural network and MLP. And we will talk about 3 characteristics. First of this characteristic is sparse weights. So we know the idea of the receptive field. We know that only neurons within the receptive field are activated by given patterns. So we can see that a neuron in the next layer is connected only to neurons in a previous layer that are within this receptive field. And kernel is smaller than the input. You can see it also here. This is the bottom-up approach. So like this is the previous layer. This is the next layer. So we can see that this neuron will affect those outputs. Contrary to MLP, where every output interacts with every input. In general, image recognition with MLP is of course possible, but we'll have a huge number of parameters, so training is more complicated. In CNN, we have partially connected layers, so it's simpler. The next characteristic is called weight sharing. We use the same weights for more than one location. So if we look at the image from the right, we can see that we have weight 1, which is just got this output. But then when we move the filter, the same weight is also used to calculate the output at different locations. So once the network learns how to extract a given pattern at one location, it will be able to extract the same pattern at different locations. In a traditional approach, each weight was used only once. Okay. And the last characteristic that I want to mention is that CNNs are equivariant to there was a question about recording. Sorry. Okay. And the last characteristic that I would like to mention is equivariant to translation. Output translates in the same way as input. So as we can see here, we have some inputs that produce some outputs, like here. But then, if we append a value before, we'll produce the same outputs, but only shifted by this translation that we used. Okay. So now we can see an example of that. So if you could please open the notebook that I sent you on the chat. I will reply to all questions later. You can also ping me on the Slack later if you have any other questions. Okay, so I hope you are able to open the notebook. So at the top, just run the cell with imports. I will skip this part. I'm sure you already know the library that we use. So at the top, we have some helper functions that I will be using. So I will just go quickly through them. The first one is used just to print the text in a formatted way. So we can see, like when we run it, we'll have a bold text or a bigger text. This is just used for visualization. The first function I use for plotting images. So for example, when we look at this cell, if we have an array, for example, with some values or with zeros, we can use the plot function. And as a first argument, we pass a list of arrays that we want to plot. So we will have our data shown. We can also display values of pixels. I limited it to arrays that are smaller than 9 by 9, only for visualization purposes. So if you want to display the values for image or data at index 0 that we passed here, let's use values on 0. It means that we'll display values for image with index 0, then index 1, like that, and so on. Another function is for downloading images from given worlds. And
could you please zoom a little bit the notebook, because due to our transmission the quality is low. So could you please zoom the Command Shift plus, Command Shift plus, Command Shift plus?
Yeah, is it better?
One time.
One more.
Wow, perfect. Wow, especially for older people like me. Thank you very much. Sorry.
Okay, sure. Okay, so we use this function, download and prepare. We can download and scale our data. So I uploaded some example images that we can now download and plot. And I use the same function for plotting them. Like here, we have a car, cake, and a baby. We can also display labels that are used in the dictionary here. So, for example, like that. We'll have labels. We can change the color map that we use. By default, it's gray, but you can use reversed gray. You can also change the range for the color map. Okay, like that. Okay, let's move to the next function. So this is for plotting curve. If we have a dictionary where each entry is a separate set of data, and then it contains another dictionary with y, x values and a label, we can pass it to this function and plot the curve. Yes. We have two entries, one training, one validation. So I will be using that for visualization of our training. Okay, so this is just the introduction. Oh, one more thing. I don't know if you set the runtime type to GPU. If no, please do this, because we'll be doing some simple training, so it might be useful. If you change it now, you will have to run the cells that just run again, because close it like that and then run all cells at once. So now we are at our first task, and we will calculate the convolution by hand at first. So I defined some kernels here with some values. We have vertical kernel and horizontal, which is a transposed version of a vertical kernel. And we have some sharpening kernels with different perceptive field sizes, 3 by 3, 5 by 5. And also we have one Laplacian kernel, which highlights regions of rapid intensity changes. So the next two cells, just please run them. You don't have to look into them for now because we want to calculate the convolution by hand and then compare with the result calculated using TensorFlow. So just run those two cells. And then we can see our task here. So if you run the cell, you will see that you have some input data and you have a kernel, and your task is to calculate the output values. So how do we do this? Maybe I will draw. So, for example, we want to calculate the output value for this 4. So we place our filter like that. So the middle of the filter covers 4. And we see that some input values are missing here. So for now, assume that they are zeros. So image inputs are 0 here, and then we apply our filter here. Change the color. So 0 from the filter will go here, then -1, 0, -1, 5, -1, 0, -1, and 0. So here we have 0, so it will produce 0, but here we have 5 multiplied by 4, which is 20, and then 0, 0, -2, 18. So the value here should be 18. So please take a second to do this. And please place I will just clear drawing, and please place your results here. So like we calculated for the first row, first value is 18. And once you're ready, you can just run the cell to see if your result is correct. You take a while. Oh, my result is not correct. I only calculated the first value. For example, for this 5 in the middle, we'll have 5 multiplied by 5, which is 25. Then we'll have 0 here, 0 here, 0 here. -3, 22, -2, 20, and then 0, 0, 0. So here we should have 20. If you don't want to do this, you just want to see the answer, you can just change show answer to true. I will give you 2 more minutes to try it. I think it's a useful exercise for you to see how it really works and to make sure you know how to slide the filter and how to multiply the values. Okay, so you can just display the answer. I hope you are able to calculate the values correctly. Okay, so now let's come back to our presentation. So I hope we all know how convolution works now. So let's see what we can do with the convolution. So the weights that we use in our kernel will determine what features are extracted. For example, we have a filter like that on the left with one vertical line of ones. So how do you think what pattern will be extracted? It will, the result of the convolution will be that all values except the vertical lines will be blurred, ignored, and the vertical lines will be highlighted. Similarly with the next filter, which has a horizontal line of ones, we'll highlight the horizontal lines in the image. Okay. So let's see how it looks on real images. So we can see that we produce feature maps that highlight the area which are most similar to our used filter. Values that correspond to the kernel are enhanced and the rest of the image is blurred. On the left we have vertical lines enhanced, and on the right we have horizontal lines enhanced. So we can easily see that by using different filters we can extract different features of our objects. Okay, so if you can go to Jupyter Notebook again, and we have our second task here. So please experiment for a second with different filters. You have a list of downloaded images. You can access them by using different indices here. So, for example, horizontal filter with the first image will produce this result. We can see that horizontal lines are enhanced. If we change it to vertical, we'll see a different result. You can use other filters as well, Laplacian. We can see that rapid intensity changes were enhanced. You can try with other images as well. I think there are 5 images, so the last index is 4. Like that. So please take a second to see. You can also plot different results at once. So like if you multiply this line and use different kernels and then pass the result to the plot images function, you'll see rows of plotted images, so maybe it will be easier for you to compare the results. And if ever of you, one of you tried running this filter with image 4, I hope you'll be able to see the hidden message here. It's an answer, great. Okay. So come back to the presentation. Okay. So till now we calculated outputs for each input value of our images, of our data. But there are 2 important parameters that we should talk about. Remember in our convolution example, when we calculated output for edge values, we had to assume that there are zeros around our image in order to be able to place the kernel, the center of the kernel on our edge value. So what we did zero padding. We we added columns, sufficient number of columns and rows filled with 0, so that it's possible to place the kernel on the edge data. And as we can see, a neuron in the next layer, here this one, is connected to outputs of neurons covered by this receptive field. And then, so it's the neuron at the corresponding location, plus minus half of the height and width of the filter. And then we move the filter to calculate next output value. But there is also a parameter which specifies the number of pixels by which we move the filter. And this parameter is called a stride. And in other words, it's the distance between two consecutive receptive fields. And stride doesn't have to be the same in both directions, so we can move a filter by different number of pixels in horizontal direction and a different number of pixels in vertical direction. So, for example, for a stride of 2, we'll calculate the output value by placing a filter here, and then we'll move it by 2 pixels. We'll skip this value. So approximately the output size will be half of the size of the input. I said approximately because it also depends on the padding. We have 2 different values of padding. Padding same, which means that the convolution layer uses 0 padding if necessary. So if we have a stride of 1, output will have the same spatial size as the input. But if we use padding valley, we won't use 0 padding, so some rows and columns might be ignored, like here, and the output size will be smaller. So let's look at the example. The formula on the top that you can see here defines our output size, but let's see in practice how it works. So I'll try to draw in a second. Yes. Okay. So we have our input here, and we want to use a stride of 1 padding valid, so we don't use 0 padding, and this is our kernel of a size 3. So what we do, we place it here, -1, 0, 1, and we calculate the output value. So it's -1, -2, it's -3. And then we move our filter by a stride of 1, so by 1. So it's -1, 0, 1. So it's -2. And then again for this location, then for this location, for this. And that's all. We can't move our filter more to the right because we don't use 0 padding. So the output size will be 5. So let's see if it's consistent with the formula. Input is 7 minus kernel size 3, 4, divided by 1. We don't use padding, so 0, and then plus 1, 5, yes. Okay, what about this example? We use a stride of 2. So we start in the same way, -1, 0, 1. So we'll have -3. But then we will skip this value, so we'll apply our filter here. We'll skip 1 and then here. So we can see that our output size will be smaller. Okay. So now we'll try another exercise. Let's open our notebook again. And take a while to try different stride and padding parameters to experiment with that. You can see here I used a stride of 1 and padding same. By default it's set to same. The stride is 4 dimensions. The first one is stride across batch, then height and across channels. But I think that stride across batch and channel is not supported for now, so just modify height and width. So, for example, if you want to use a stride of 2, and then display this result, you'll see that we skip every other value, so we only extract a limited number of features. The resolution is lower. You can also use valid padding. You can also change the filter if you want to see how it works with a different filter. So we have valid filter. So we will see that the output dimension is smaller. Spatial dimension. We'll change to 3 columns. Something one. Oh yeah, because I have one more here. It shouldn't be here. Okay. Yes. So it's most visible on this Mercedes logo here. We can see that a part of it is not visible. And if you're interested, you can also print the shape, like here. So this is valid padding. So we can see for a stride of 2, it's approximately half of the size. And then, I think, yeah, here it's exactly the half because we use the same padding. And here for a valid padding, we also have a smaller dimension because we don't use 0 padding, so we skip the edge values. Okay. So now let's come back to the presentation. What's very important to say is that for now we were using predefined kernels. In fact, we don't do this. We let the network learn what patterns are important. So we initialize our filters with random values, and then during the propagation we update the weights so that the network will learn what is important for a given task. And some receptive fields are larger than others, and in this way they can react to more complex patterns that are a combination of lower level patterns. So for example, given the pixel values, we can recognize edges, like here, by comparing brightness of neighboring values. Then given the edges, we can look for contours. When we have contours, we can look for some basic shapes Then, given basic shapes, we can look for some of the parts, and then finally we can have our final objects, our final categories. What's also important is the depth of representation. So for now, for all our examples, we used input of a depth of 1 because we used grayscale data. But in fact, the representation can be deeper. So for example, when we have RGB image, we'll have filter which covers the same receptive field, but is extended across the depth of this layer. So as we can see in this animation, we have a filter which covers the whole input depth to calculate the output value. Then it's moved without changing weights because we have a weight sharing approach. It's moved across the image to calculate another output value, and so on and so on. And then we apply another filter which may have different weights to calculate another feature map. And in this way, we create a cascade of different feature maps of different filters in order to detect different patterns. So at first we have a very simple patterns, that then they are combined to build more complex patterns, and so on and so on. In this way, we can represent a very complicated mapping by a stack, a sequence of nested simpler mappings. And this approach turned out to be very effective in simulating hierarchical structure of objects and in real-life applications. Okay. Another important operation used in CNNs is called pooling. What's important, pooling doesn't have weights. It is aggregation function to calculate output within the receptive field. So if we have a receptive field, it also has a kernel size. It also has a padding and the stride. And how does it work? The pooling helps to make the input invariant to small translations because it extracts only a specific value within the receptive field. It depends on the aggregation function that we use. We'll see in a second what can we use, but for example, we can use a max pooling, so it will extract the max value within the receptive field. By using pooling, we can reduce the spatial dimension, so reduce the risk of overfitting of the model, a situation where the model is very good on our training data, but can generalize well to new examples. The variance is high. And what's also important, pooling works on every channel separately, so the output depth is the same as input, but we can reduce the spatial dimension. So let's look at this example. So this is max pooling. So we'll pass only the maximum value within the receptive field. So we have a receptive field which covers these 4 values here. And we will output 8 because this is the maximum value. Then the other one will output 4, here we'll output 6, and here we'll output 8. Maximum pooling might be very destructive because it outputs only a single value within the receptive field, but on the other hand, it extracts very extreme features, so it turns to be very efficient. Okay. So I will clear this drawing. Okay, and the next pooling is average pooling. So here we output the average of all values within the receptive field. So here we'll have 8 plus 2 plus 2, 12 divided by 4, which is 3. 8 divided by 4, which is 2. Here we'll have 3. And then here also we'll have 3. And as we can see, it creates, it may create a very generalized output because it takes the average. So we may blur our features, but sometimes it's also very useful. Usually it's hard to say which pooling is better, so you can always try. I think that max pooling is used more often, but for example, when we have the last layer and we want to turn it into a single vector, which will represent the features for the image as a whole, we usually use the average pooling. You can always experiment and see what works good for you. Okay. So now let's go again to our Jupyter notebook. And we'll have our fourth task. We would like to calculate the output size of a model, which consists of 4 operations defined here. So we have a convolution, pooling, another convolution, and pooling. Here, let's use pooling valid. And you can calculate it manually, or you can also utilize the apply convolution function. It applies convolution, but you can also use it for pooling because we don't care about the output values, we just care about the size. So if you just want to say the size of the output, you can utilize this one as well. So I will give you a second to try it on your own. And once you're ready, maybe you can type the answer in the chat window so that I will know that you managed to do this. So we have first convolution with 16 filters of a size 3 by 3 and a stride of 1. The input is of a size 22 by 22 by 3. We'll know that each of those filters will work on the whole input depth, and we'll apply 16 of those filters. So we'll have a depth of 16 because we have 16 filters. What about the width and the height of the representation? We use the padding valid, so we don't use 0 padding, so we can assume that the output will be smaller than 22 by 22, and we use the stride of 1. So if our kernel has a size of 3, we'll at first apply it on the third column, on the second column and row, because we don't have 0 padding, so we can apply it on the first column and the first row, and then we'll move it across our image until the 27 column. So we'll have 26 by 26. Okay. I don't know if any one of you is ready. If you're ready, please send the answer on the chat. Okay, so after that we have a pooling. We know that pooling operates on each channel separately, so the depth will be the same. What about the width and the height? We have a kernel size of 5 and a stride of 3. So we will start at the third column and third row, and then we'll move it by 3. So third and 6, 9, 12, 15, 18, 21, 24. That's the last where we can apply the filter. So it's 8 times. So 8 by 8. Okay. I think this exercise is very useful to understand both those parameters. So you could try it. Then we have 32 filters. They all operate on the whole input depth. So we'll have a depth of 32. And then filters have a size of 3. The pooling operation, yes, okay. So we had the input of a size 26 by 26. And now we want to apply a kernel of a size 5 by 5. And the padding is valid, so we don't use 0 padding. So we can't apply it on the first column, and we can't apply the second column, so we'll see those. We can apply it on the third column and third row. And then we move it by 3. So third column, then by 6, 9, and so on and so on. And if you calculate it, the last column that you'll apply will be 24. So it's 8 times. So that's why it's 8 by 8. You can also use the formula that we had on one of the slides. Okay, and then we have again convolution, strides of 1, filter size 3 by 3, padding same. If we know that the padding is same, we at once we have one answer. I think it's too much. 5 by 5 is too much. So padding is same, so the dimension is same, 8 by 8. 6 by 6 is too much. Okay, and then we have pooling with a kernel size 3 by 3, strides 5, padding valid. So we know that the spatial dimension will be reduced by the depth but the depth will be the same, so it's 32. That's correct. Both of the answers on the chat have the depth correct, but the width and height is not correct. Yes, we have one good answer, Timothy. Is correct. Yes, it's 2 by 2. So we had 8 by 8. And then we have a kernel of a size 3 by 3 and a stride of 5. So we will start on the second row and second column. And then we will move the filter by 5. Can the stride be bigger than the kernel size? Yes, it can be bigger. So we'll start at the second row, second column. So we'll have one output value, and then we'll move by 5, which will end up at 7 row and 7 column. And we can't move the filter more, so it's 2 by 2. If you are interested in checking whether it's correct, you can apply a sequence of functions that I had there. Just copy paste. So we have 3 by 3, 16 kernels, stride of 1, valid, and then 5 by 5, stride 3, valid, and same, valid, and kernel size 3 by 3, 3 by 3, stride 1 by 1, 5 by 5. So check this correct. Yes, it's 2 by 2 by 32. Okay. So if you want, you can experiment later, change some parameters, and try it on your own to make sure you understand it correctly. I will reply to all questions later. Okay, so just to see how it all looks together, we have a structure which resembles a pyramid. So at each level, we can increase the depth by using more number of filters. So we create deeper representations. And then by using straight and pooling, we can use spatial dimension. We also, after each convolution, we apply activation to introduce nonlinearities and solve nonlinear problems. And usually we use many hidden layers, so we have a deep network. And at first we extract low-level features, for example, edges that are then assembled into more complex features in the next layer. I'm sure you remember from the previous lecture that at the end, flatten the representation fully connected to the dense layer of the size of our output categories and apply softmax to turn our scores into probabilities. And if it's inference, we just have a prediction vector, so we know what category we have in our image. And if it's a training, we can use this information to calculate the loss using our labels in a supervised setting. They can be one-hot encoded, they don't have to be one-hot encoded. And then we update the weights using, for example, stochastic gradient descent. And then we pass another mini batch of training examples, and then we again update the model and so on and so on. Okay. And before we implement a simple CNN, I would like to briefly mention some types of convolutions. So first convolution is known as one-by-one. This convolution doesn't look at the patch, doesn't look at the receptive field, but the receptive field just covers one pixel. So at first, it may just seem to be a multiplication. We take the input value we multiply it by kernel value, and we produce the output. So it takes only scaling of the value, why it's even useful. But when we look at this representation, it may become more clear. So we know that we operate on the whole depth of the input. So we have the whole vector that is connected to the filter, and then we can apply linearity. And if we use more number of filters, we'll have a structure which looks like that. We'll have a filter which is connected to all input values, and then another filter which is connected to all input values, and so on and so on. So it looks similar to a fully connected layer. In fact, it looks exactly like a fully connected layer. So that's why it's usually called networking network. And by using different number of filters, we can increase or decrease the depth of representation and introduce nonlinearities. So this operation can act like channel-wise pooling. And for example, it was used in the inception network and turned out to be very useful there. Another convolution is 3D convolution. So in this type of convolution, we move filter in additional dimension. If we have, for example, temporal data, we move it in a temporal dimension as well. So we have a filter which we move on our frame. For example, assume we have a sequence of frames, so we have a video. So we move our filter on the first frame, and then also we take the value of the next frame and so on to calculate the output. And this convolution is useful, for example, in 3-dimensional medical data. Another type of convolution is called the convolution. So in a standard convolution, we produce output of the same size or of a smaller size than the input, like here. But imagine that we have a way to take a smaller input and upsample it, extend it to produce more data. In these cases, we can use convolution, which is alternative approach to, for example, B-cubic interpolation. And this convolution is also known as transport convolution. It will become more clear if we look at the example. So this is a standard convolution here on the left. We have our input image, we have our kernel, and we produce output. We don't use zero padding, so the output is smaller. But now let's represent it in a way that a computer actually computes it. So we create another representation of our kernel values, where each row contains values of the filter. So for example, like here, the blue box, we have 3 middle values of our kernel here, and then we skip 1 because we skip this column, and then we have another 3, here we have those 3, the first 3. And then the stride is 1, so we move by 1, and we have the same representation here. We have to flatten the image to multiply kernel by it, and we produce the output, like here, 2 by 2. We see that when we reshape it, we will have our output here. And now see what will happen if we transpose the kernel. So here we have the same kernel, but it's just transposed. And we have input of a smaller size, and we want to expand it. So we can see that by using the same filter and a smaller output, we can expand it and create representation with a bigger spatial dimension. So this is a transport convolution, and it's used, for example, in UNet segmentation network, used for medical image segmentation. Another convolution is called unshared convolution. So in a standard convolution, we use the same weights of a kernel, and we slide it on our image. In shared convolution, we use a different set of weights for each location. And this convolution is useful when we know that one feature is present in one location, but probably it's not present in other locations. For example, imagine an image of a face. We know that a nose is present in one location. Okay, and another convolution, tiled convolution. This is somewhere between unshared and standard convolution. Weights are spare, but we have a limited set of weights that we rotate through the image as we move in space. So nearby neurons are untied. They have different weights, but far apart neurons are tied. In the standard convolution, in the second layer, we are constrained to pull over translation of the same base of the same function. But in the tiled convolution, we have different functions so that we pull over. So we can learn more complex relations, and it turned out that this convolution helps with dealing with some rotational and scale variances. Another convolution, spatially separable convolution, is used for optimization. So this convolution, we just represent the kernel by smaller kernels, multiplication of smaller kernels. And in this way, instead of 9 multiplications, we have 2 convolutions with 3 multiplications each. Another convolution, which is also used for optimization of computations, is called depthwise separable convolution. It consists of 2 steps. So we have at first a depthwise convolution, and then we have one-by-one convolution. Imagine that we have an image of some size. We want to apply a standard convolution to produce a deep representation, for example, of a depth 128. So if we look here, if we want to produce output of a depth 128, so we'll have 128 filters. Each will operate on, they have a size 5 by 5, for example. It will operate on the whole input depth. We have, for example, 3 channels. And, for example, the input is of a size 12 by 12. So we will move the filter 8 times. So we'll have so many multiplications, more than 600,000 multiplications. Now let's look at the depthwise separable convolution. So at first we use depthwise convolution. Depthwise convolution operates on a single channel only. So if input has a depth of 3, our kernel will operate only on the first channel at first, then another filter on the other one, and the third on the third one. So we'll have 3 filters of a size 5 by 5 by 1. They operate on one channel only, and we will move them 8 by 8 times. And then we want to expand the depth. So we know already that we can use 1-by-1 convolution to expand the depth. So we'll have 128 1-by-1 filters that will operate on the whole input depth of 3, and we'll move them 8 by 8 times. So as a result, we have less than 30,000 multiplications. So as we can see, we reduce the computational complexity of the model. And the last convolution that I would like to mention is called dilated convolution, and it uses a kernel which is spaced out on a larger receptive field. And we define dilation for this convolution. So dilation of 2 would mean that every other pixel is skipped. So in this way, we can integrate knowledge of a wider context. And it has been shown to be very efficient for image segmentation. This third column uses dilated convolution. So we can see that the extracted shapes are much more detailed. And I know that all of this type of convolution is just a brief overview. So if you are interested, please look more into them. We have a limited time, so I can just mention them. And I really would like you to try building the convolutional model yourself. So we'll go into it in a second. But one more thing that I would like to mention is that there are different variations of convolutions and of model structures, and the invention in this field have significantly progressed since the invention of deep learning in 2012 with AlexNet. AlexNet was a simple 8-layer convolutional model which allowed for reducing error of image classification significantly compared to previous shallow networks. Then, across next years, it has been shown that deeper models lead to even better accuracy, but specific model architecture is also important. For example, the use of residual connection. The accuracy of a ResNet was very high, I recommend you checking out the ResNet network. Another important part of our research focuses on more quantization and optimization using specific operations. It is becoming very popular because of edge applications, for example, in autonomous driving, where we have power consumption limitations, or in smart home devices when we have resource-constrained devices. What is also important is that CNN is used not only for image classification, it can be used also as a backbone, as a feature extractor for other computer vision tasks. And we'll learn more about segmentation on Wednesday. But for now, I'd like to focus on image classification only and build a simple CNN to recognize images. So please go to your notebook again. And our task will be to implement and train a simple model, and then we'll try to prevent it from overfitting, and we'll try to improve accuracy by some tricks without changing the model structure. So I will use rock, paper, scissors dataset, and I will use the TensorFlow dataset API. It's very slow API. It contains different publicly available datasets that are prepared and available for you to use. So I recommend you checking out that as well. And we'll create a training set. So we will use split train. We'll shuffle files to ensure that each data pass creates independent change to the model and is not biased by a previous update. And we use a supervised setting, so we'll use labels to update our model. And we load the data set with information about it. And then we create a validation set. There is no explicit validation set in this data set, so I use a part of a test set for that. It may be also good to use a part of a train set for validation, but I wanted to have as many examples as possible for training, so I use a part of validation data set. Okay, so if you run the cell, you will see that it downloads and prepares the data set. And yes, we can print out information about it. So for example, number of train examples, number of validation examples, number of classes. It's all available in the info that we have here after running this command. And this is rock, paper, scissors, so we have 3 classes here. We can display images using our plot images function. See how they look. I convert them to NumPy array because this is what my function expects as input. Okay, we see that we have 3 papers here. Okay, and then we will further prepare our data set. So what we'll do, we'll create a mini batches for our training. So we'll split the data set into elements of specific sizes. We'll also use prefetch option. This option is used for better performance because by using it, the data preprocessing overlaps with the model execution. So the data can be used immediately once the given step is done. We don't have to wait for the preparation. And we'll additionally shuffle the training set. So at each epoch we'll be sampling elements from the buffer and replacing them with new elements. And here, if you are interested, you can just print and see how it looks. So like in the preferred, we'll have a batch, and before we had a single example only. Okay, and now we will build a simple model. I'm using Keras API and sequential model. So we'll just I run it, but there is a to-do for you to do. So I'm using sequential, so we'll group a linear stack of layers. So please add to convolution to max pooling layers. You can check their definition by clicking on those links. Of course, you could build deeper models, but we want to train it and we have a limited time, so advise to use layers for now, for me. And then, as we have seen, we will flatten the representation and connect it to the fully connected layer, and then to our output categories. So the last layer will have a size of 3 because we have 3 classes. So how do you do it? You can use layers convolution conv to the function, and then you define a number of filters, for example 16, and a kernel size, for example 5. I will use the padding same activation real. This is a very common activation function used in deep learning because it has a simple derivative. But sometimes it may suffer from, because we skip all values below 0, it may suffer from dying free will problems. So, for example, sometimes you use leaky real, so you have also some linear function below zeros. Okay, and that's for sure. And for the first layer, we also have to define the input shape. We have it defined there earlier, so I can just use it like that. Okay, this is our first convolution. Then we want to add max pooling. We can use default parameters for max pooling. I think it's by default it's a kernel size of 2 and stride of 2 as well. And then we want to add another convolution layer to the. I want to use more filters. You can use different parameters than I'm using. We experiment and we check different parameters and see how the model works with them. Okay. And then one more pooling layer. About protocol. And then we use compile function to build the model. I will use Adam optimizer. I wish we had more time to cover different optimizers as well, but again, we have a limited time. But just in a nutshell, Adam is an effective extension to stochastic gradient descent that combines momentum with RMS prop. RMS prop is another optimizer which allows us for restricting gradient oscillations. We should also read about them. And we'll evaluate accuracy during the training. So hopefully if we run it now, it will work. Okay, and by using summary, we can print out the structure of our model. we can see that the last layer has dimension of 3, so we have our 3 categories. So once you're ready, you can train the model, and hopefully you will see that the accuracy is even low or it drops, so that we'll be able to improve it in the next step. It will take a while. Okay. And the results are pretty good. They shouldn't be that good. And maybe if you use a smaller data set, you'll see overfitting better. But we can see that the accuracy of a trained set is 100, which usually is not possible. So when I assume that the model overfitted, the accuracy on the validation set is also quite high. So maybe the model also overfitted the validation set. You can also experiment and use only a half of a training data set here, before, like here, to see that the validation accuracy drops. But let's see if we can improve this result by using some techniques. So if you go to the next cell, the first task is to normalize the data. So it's usually useful to normalize the data so that all features contribute equally to the result and that gradient steps are more. So we can, for example, normalize the data set to the range from 0 to 1. So do it like that. You can check more about data normalization under this link. So we can use layers, experimental, processing, scaling. And it will be the first layer in our model, so please define input shape. And as a first parameter, use the range that you would like to use. I'll give you a second to try it on your own. And after you run the cell, you should see that the range of data changed. You can also normalize data from -1 to 1. And give me a second to think about how to do this. Okay. Yeah. So we can see that our data is normalized. So this will ensure that we'll have all inputs in the same range. Okay. Another thing that we can do is data augmentation. So your task is to add data augmentation. You can again check different augmentation option under this link. Augmentation is used to increase the size of training examples by adding different transformations to images, like flipping or zooming or rotation of images. And you can use many of them. And to do this, you can use again the sequential class. So do it like that, and pre-processing. If you check this link, there are different options. For example, random, flip, float, horizontal or vertical. If you want, also define the input shape because it's the first layer. And you can stack different layers on top of each other so that different transformation will be applied. For example, layers on top of pre-processing and on rotation. And as argument rotation factor, or it's also random zoom factor, and so on. So after you do this, and if you run the cell, you will see what transformation has been applied. So we have our input image, and then it's rotated at different angles, it's zoomed. In this way, we have probably we will achieve better results because we increase the training data set. And the last thing that we will do is a dropout. Dropout is another regularization technique which allows us to prevent from overfitting. How it works, maybe I will draw it here. So like imagine that you have a network that you train. These are your neurons and they are connected to other neurons in the next layer. And what dropout does, it randomly removes some neurons, like that, for example, this. In this way, the network may never rely on any neuron to be present, and it can generalize better. So you can define dropout here. It's layers, dropout, and the rate that we would like to drop. Okay, so here we would like to create a modified model. So I will go and just copy our convolution link layers. And place them here. And before convolution, we want to apply normalization. So like that, defined before. and then data augmentation. And then we would like to apply dropout as well. It doesn't really matter. You can place the dropout everywhere you like, but it's really useful to place it after a layer with many parameters because it's more likely to overfit. So, for example, here. And when we run the cell, the rest is the same. We'll see that there are added layer here. And then we can train the model. Hopefully we'll get better results. Yes, we see. I think that before we got the accuracy of 82 in the validation set, we are better in just 3 epochs. We see that the accuracy in the training set changes, so probably it's not overfitted. Of course, just to check the real performance of the model after the training on a test set, a set that has not been presented to the model before, to see how it really works. But for simplicity, let's just focus on this one now. Okay. One more. Okay, and we can plot the results. Yeah, so like here we can see that results were improved without changing the model structure, but by just using some tricks and techniques. So let's go back to the presentation for a second. I would like to show you one more thing. So this is the plot that I got before. So we see there was a huge difference between the orange one. The line was without regularization. The red one was with. So there was a bigger difference. Okay. And right now, imagine you have your own data set that you would like to train the model with. I don't know if you are familiar with Big Bang Theory episode where Sheldon explained that by using only 3 categories, rock, paper, scissors, we'll end up in a tie when we play with friends. So we should use more categories. I will show you it in a while. What we can do, we want to use our own data set, but we don't have time or resources to collect and annotate it. In this case, we can use approach known as transfer learning. So we can repropose the existing model to a novel task. So we take the model that is trained on a huge data set. For example, here this is the description model, and it's already trained to recognize some categories. So what we can do is we can keep all layers untouched and just train final few layers of the model to modify it to our task. I collected some of the examples. I placed it under this link. The way how it's organized, it's that you have different directories where each directory name represents the category name, and then you place images in those directories. And at first you can see how you can build records using your own data set. So you can use function from Keras, again, preprocessing, create image dataset from directory, and just pass this directory to it. So we'll create our training and validation set. Similarly as before, we will optimize and shuffle data. And we can display our images here. So we can see paper, rock, and paper. Okay, and at first we'll train the model, so we'll train all layers of the model. Here I chose the mobile net, which uses the twice surveyable convolutions, and it is very efficient for mobile applications because of that, without impacting accuracy significantly. You can also try with other models, for example, ResNet. In applications, there are different models available. So we set include top as false because we want to have our own fully connected layer with our own categories. And then we don't load any weights, so we'll be able to train the whole model. We set it as trainable true. And you can see in the summary all the layers that the model has. Similar as before, I will use pre-processing here. I use pre-processing from the mobile net because it's slightly different. It's from -1 to 1. And also some data augmentation dropout. And then we want to adjust it to our data set. So we just have input layer of our size. Then we pre-process the input and use data augmentation. Then we use our downloaded, our prepared model and training as true. And as the output from this model, we have a block of precise 7 by 7 by the depth number of features. But we want to have only one vector for the whole image to produce classification of this image. So we use global average pooling to squeeze it into one vector. And then we apply dropout and a dense layer with number of our categories. We use a lower learning rate because I want to compare like 1-to-1 with the model which will be fine-tuned. So in fine-tuning, we use lower learning rate to just adjust weights. Yeah, we can see that after the mobile net, it was changed to one vector and then connected to 5 output categories. And you can try it here. You can see that accuracy is pretty poor, 25%. Maybe if we train longer, we'll get better, but we have a very small data set, so probably it will overfit. Okay, so it's done 43%. You can plot it again. And now what we'll do, we'll fine-tune the model. So again, it's the same model. We also don't include the top because we have our own categories, but this time we use the weights of ImageNet. This is a huge data set with 1,000 categories. So this model is already trained on that and has good accuracy on that, so we'll just retrain the final layers. You can set how many layers you want to retrain here. For example, I will retrain top 60 layers. Okay. And you can see that only some parameters are trained, some parameters are not trained here. And similarly as before, we use global average pooling and dropout. And we can see the summary of the model, and we can train it. Hopefully we'll get better accuracy because we reuse some of existing, we just modify it to our task. You can see that we already have 68%, which is already better. Okay. So if we plot it, we can see that in a shorter time, we achieved better accuracy by using the fine-tuning approach. So that's why it's often used in case when you have a limited time for training or limited size of your dataset. Yes, that was the last example that I wanted to show you. Thank you very much.